So concentration boundary layer. So just as velocity and thermal boundary layers develop when there's a velocity or temperature difference between a surface and the free stream, a concentration boundary layer also develops whenever there's a difference in species concentration between the surface and the free stream as well. So consider the flow of a binary mixture of species A and B over a flat plate, and let the concentration of A, S be the molar concentration of species A at the surface. So over here at the surface, you have the concentration of species A, and you have concentration of species A, infinity. Here is just referring to the molar concentration of species A in the free stream, which is what is in this mixture that is flowing into above the flat plate. And at the leading edge, the free stream concentration profile is known because at the leading edge, you just have this mixture. So everywhere in this mixture, you're going to have this uniform concentration of the A infinity, which is the concentration of the free stream concentration. Okay, so what happens is when the fluid comes into contact with the surface, then the concentration of species A at the wall is fixed at that particular concentration. And if that particular concentration is not the same as the concentration of the mixture that is flowing over it, then you have a concentration gradient that develops normal to the surface again. So what happens is that you have fluid particles near the wall exchange species with neighboring fluid layers by molecular diffusion, and you also have simultaneously the bulk flow carries species downstream by advection. So the region of the fluid where the concentration gradient exists is called the concentration boundary layer. So this is exactly the same thing as the velocity and the thermal boundary layer that we've discussed. So the mass transfer mechanism at the wall. So at the surface, you have the fluid velocity is 0 because of the no slip condition. Therefore, species transfer at the wall occurs only because of molecular diffusion. And so the local molar flux of species A at the surface is given by Fick's law. This is similar to the conduction that we've identified in the thermal boundary layer that occurred at the surface. The equivalent of that in terms of mass transfer is Fick's law, whereby at the surface, we know that the molar flux is equal to -1 multiplied by the molecular diffusion coefficient multiplied by the concentration gradient in the y direction evaluated at the surface. We also know that, analogous to Newton's law of cooling, the molar flux may also be written at the molar flux is equal to the mass transfer convection coefficient multiplied by the difference in the concentration from the surface to the bulk. Now, if we do the same thing that we did with the thermal boundary layer analysis, so if we combine these two expressions, we show that the local mass transfer coefficient depends directly on this gradient at the wall. So you have this local mass transfer coefficient is equal to -1 times the molecular diffusion coefficient over the difference in the concentrations from the surface to the bulk, all that multiplied by the gradient of the concentration at the wall. Now, before seeing what we're going to do with this, which is going to be pretty similar to what we did with the thermal boundary layer analysis, let's look at the boundary layer thickness. So as distance from the leading edge increases, then you have the region of the fluid affected by the surface concentration. It extends further into the stream, and the concentration boundary layer, as you can see here, thickens. the concentration gradient at the wall decreases, and it decreases for all the same reasons that we've already discussed previously. So we know that as the Reynolds number increases, we have more of inertial forces. And if you have more of inertial forces, you'll have better mixing. Now, because the concentration difference between the surface of the plate and the bulk is constant, then decreasing wall concentration gradient leads to a decreasing molar flux, which is understandable, and that's because the mass transfer coefficient decreases.